Let's take a look now at section 2.5. We've been working with inequalities, trying to get an understanding as to how they work, realizing that they can have multiple answers and how to graph them and where they are on the number line and how to recognize greater than and less than, and greater than or equal or less than or equal. And so now we're going to move forward a little bit. And in this lesson, we're going to understand and solve absolute values. We're going to solve linear absolute value equations. And we've already looked at those a little bit. I think if you remember, we talked about absolute value equations in chapter 1. And we learned how to graph them using the XY axis. We're going to solve and graph linear absolute value inequalities on a number line, and then we're going to graph linear absolute values and use the graph to determine solutions. And when we talk about determining solutions, we're going to have a situation where we're going to have multiple solutions to these. Then the key terms we're going to deal with, the opposites, absolute values, the linear absolute value equation, linear absolute value inequalities, and equivalent compound inequalities. And this little section right here on this page talks about rules and regulations, and we're really going to be involved with those as we deal with these absolute values. Of course, everything in math does deal with rules and regulations, and so this just talks about some rules that are in the NBA or the National Hockey League or the NFL, and what kinds of things you can see. And you can read it if you want. Here we're going to analyze the idea of opposites. We've got a -2 and a 2, and you'll see that they are marked here on the number line. This one right here, and this one right here. Sorry. And what you'll notice is that the -2 and the 2 are the same distance away from 0. And so when we start talking about absolute value and really taking a look at it, what we're dealing with is what is the distance from 0. The negative has nothing to do with it, and the positive has nothing to do with it. It's the distance away from 0. If I get in a car and drive from here to Salt Lake with the car pointing frontwards, and I get in the car and drive backwards to Salt Lake, I still go the same distance. It does not matter which direction I'm facing or which direction that I'm going. And so a -2 and a 2 are the same distance from 0. A -2/3 and 2/3 are the same distance. And that's basically what you're analyzing here. And to describe the relationship between the two numbers, I think I've given you a really good hint there. And then here it uses the word distance for certain how far away they appear from 0. So now we're going to talk about things called opposites. Two numbers that are equidistant from 0 but are in different directions are considered opposites. And the absolute value of that is how far it is from 0. And so you see these lines right here. Absolute value of -2 is equal to, well, what is its distance from 0? Well, distance is never ever negative, and so the distance -2 is from 0 is 2. Now if I put in the absolute value of 2, what is its distance from 0? Well, its distance from 0 is also 2. And so the idea of absolute value, the distance it is away from 0. This is just a set of problems now, 6A through F, on establishing absolute value. And then 7A through D, just determine the solutions to each one. Where is x equals 5 on the number line? Where is the absolute value of x on the number line? Be careful with this one. Be careful with it. Be careful with it, because the absolute value is going to have two answers to it. Now, here we've got a situation where we're going to be judging whether things are too little or too big or too heavy or not heavy enough. And so if I just draw a line here, here it talks about a baseball. And so let's say the baseball has to weigh this much, whatever it might be. Well, there's a tolerance. I can have it weigh a little bit more, or I can have it weigh a little bit less. But if it's beyond this amount here or this amount here, then it does not qualify at all for being used as a baseball. And so we've got a certain weight here of 145 point, that's not a very good 145.045, ran out of room, sorry. And it can be as high as up to here, or as low, and I'm going to put this in a different color, as high as up to here, or as low as down to here. That's the tolerance that it has. And if you know anything about machinery and machine shops, etc., you know that there's a certain tolerance that can be used when you machine something, or that you create something a certain height or weight or circumference or anything like that. And so these problems right here on this particular page ask you to examine how heavy a ball could be or how light a ball could be within these tolerances. And so hopefully I've given you some idea here. This is a plus and this is going to be a minus. On this page we have a situation where we're going to learn how to solve inequalities. Well, I'm sorry, absolute values. I'm going to use the exact example I have here. The absolute value of x minus 1 equals 6. And here's how you do these. You turn those absolute value signs into parentheses. And since an absolute value can have a distance to the left of 0 and a distance to the right of 0, what we're going to do is here is the distance to the left of 0. Okay, and now we have learned to get rid of the parentheses, so we're going to multiply everything by -1. So the -1 times the +1 is a -1, and the x comes along for the ride. We then have a -1 times a -1 is a +1. That's equal to 6. And now we just undo the problem. So we're going to subtract 1 from both sides. So a -x equals 5. And then x equals -5. That's one of the answers. Then what we're going to do is we're going to take that absolute value and we're going to absolute value signs, and we're going to change this into a positive x plus 1 equals 6. When we multiply to get rid of the parentheses, a positive 1 times a positive 1 is a 1x. We don't write down the 1. And a positive 1 times a positive 1 is a 1 equals 6. And then we subtract 1 from both sides, so x equals 5. And so my two answers are x can equal 5 and x can equal -5. Now I don't want you to get the idea that it always is going to be the same number with just a positive or a negative. But that's how you do these problems. You set up two different equations and solve them one at a time. One of the equations is positive, and one of the equations will be negative, and you come up with two separate answers. So here we just have a set of problems for you to work. You'll do them twice. You'll put x plus 7 with a negative in front of it, and x plus 7 with a positive in front of it, and then solve it and come up with the two solutions. And then here on problem number 7, you get a chance to analyze an equation, and you've got 4 different people analyzing it, and you need to come up and find out which one of these analyses is correct. So this parts A and B are from the previous page, And then number 8, again, just a set of problems for you to work. Here's another set of problems exactly like the ones that we just did. You can now deal with the linear absolute value inequality, and we're going to talk about that baseball that we talked about in the previous section. So we're going to write a linear absolute value inequality to represent all baseball weights that are written within the specifications. So you're going to have something like this. You're going to have some value here is going to be less than or equal to the weight, call it W, which is less than or equal to some other value. What are these two lower and upper limits? We should have figured that out previously, okay? So now we're going to answer some questions, determine if each baseball has an acceptable weight, and explain why 147 does or doesn't work, why does 140.8 work or doesn't work, and why does 148.34 work or doesn't work. You've got the numbers from the previous section to plug in here to see if they are going to weigh. We know that W has a specific weight to it, and that is the weight that we're looking for, but we have these tolerances that W can be within. So now D just talks about a weight of a ball, 141.75. Does that work or does it not work? And then here again in number 3, I gave you this equation a little bit earlier. This is what it should look like. Plot things on the number line. Raymond is going to throw away the baseballs that don't match, and how many of the baseballs represented can he throw away, and then graph the inequality on the number line. We're going to expand this now just a little bit into baseballs that are used in Little League. Little League baseballs are a little bit smaller and weigh a different amount, and so you're going to fill out this table with the possibilities of whether they will work or not work. And as you know, I don't really worry too much about the units, what's going to be said there, but certainly we need to fill in the numbers correctly. Here we're going to graph this absolute value on the graphing line. You can use your graphing calculator, then you can sketch that graph here on the coordinate plane. And then 6A and B, determine the diameters of all Little League baseballs that fit within the specifications. Now there's something unique here. This is a little bit different. Right here, we see that the starting point is 0, but see that little jagged line there? That means that we're skipping a whole ton of numbers, and we're going to start with 5. In other words, we don't want to go to 0, 0.5, 1, 1.5, 2, 2.5. We know that it needs to be bigger than 5, and so we're going to start right at 5 and go 5, 5.5, 6, 6.5, and fit it into the graph that way. A little bit of a different look for you, but certainly something that you should be able to figure out. We're just narrowing down or shrinking down the graph. So here in problem 7A and B, we're going to determine whether or not a baseball can be sold or cannot be sold because it sits in the measurement, within the measurement or not within the measurement of the tolerances of the baseball. Now this has to do with Little League, okay? Now the talk, we want to do the talk on this one. We're going to talk about an equivalent compound inequality. And this table right here gives us all sorts of really good information about absolute value inequalities, the equivalent compound inequalities, and those types of things. You will use this table to help solve the other problems. So for example, this problem right here, or this example, the absolute value of A times X plus B is less than C, looks very similar to that one right there. Where in this problem, 1A, the A is equal to 1, B is equal to 3, and C is that 4. So you ought to be able to take this and apply it right there. And you'll see this back and forth. you may have to flip the pages back and forth to see which ones match up. So here we're going to solve these problems. Let me give you a hint on this first one. You got 6 is less than or equal to a negative 2x minus 4. And you got 6 is less than or equal to 2x minus 4. There are my two equations, a positive equation and a negative equation. And you're going to get rid of the parentheses, solve the problem. Remember, when you multiply or divide by a negative number, what happens to the signs? And that's how you're going to do all of these. Set them up with two possibilities, the positive side and the negative side, solve them and graph them. Some of these I think will be ands, and some of these will be ors. So now on to 2.6, final section in this chapter. You'll notice that there's no key terms, but there are some learning goals that we want to take a look at and make certain that we understand what's going to take place. We want to identify the appropriate function to represent a problem situation, determine the solutions to linear functions using intersection points. Those intersection points are where they're going to cross. We may be doing some shading. We have used intersection points on our calculators, so we ought to be fairly familiar with those. We want to determine solutions to nonlinear functions using the intersection points. What are the actual numbers that work? We also want to describe advantages and disadvantages of using technology, different methods to solve functions with and without technology. And is it going to always be better to use technology, or are there times when just human nature or human logic will work just fine? Okay, we come to a real-world situation. We're going to have a barbecue, and you're buying food, and you're going to be buying hot dogs, and you're going to be buying hamburgers. And the scenario tells us that we've already purchased 3 packs of hot dogs, and they cost $2.29 a pack. So maybe what you need to do is multiply 3 times $2.29 to see what you've spent. You also need to buy the ground meat for hamburgers, and it sells for $2.99 a pound, but you're unsure of how many pounds to buy. You must determine the total cost of your shopping trip to know if you stayed within your budget. And so here it's given us some problems, some equations right here, things that we can take a look at, and then we want to choose which function in number 1 to represent this problem situation. Why would you choose it, and did it work out correctly? And then of course we've got a table here that we need to fill out, and you'll have 3 things. We've done these so many times before that I think you know exactly how to take care of it. Here we're going to graph it from the previous page, and now we're going to apply a specific number. Consider the total bill of $13.45. So estimate how much ground beef you purchased, and then you can determine the exact amount by plugging it into the equations that we got from the other page. And then number 5, based on the number of people coming, you decide to buy 6 pounds of ground beef for the hamburgers. And if your budget is $225, do you have enough money? And tell me why or why not. If you do have enough, how much is left over? If you don't, how much more will you need? Another problem just like it, the company bought a new bulldozer for $125,000. The heavy equipment loses 1/5 of its value each year. So which of these equations is going to satisfy you? And then fill out this table again. I know we're all getting sick and tired of tables, but that's what this is anyway, so it doesn't really matter. If you like it or don't, here it is. And then you're just going to use the equation from number 1 to do number 2. Make sure you get the right equation. Here we're going to just draw now the graph of what we just put together. And then number 4, A and B, answer the question. And at what point in time will the bulldozer be worth nothing? That's you're going to subtract rates from that yearly to figure out at what point in time will it no longer have any value. In this particular scenario, we have a gymnastics meet. Some of you are familiar with gymnastics, that after you do your routine, you need to do what is called stick the landing. It can cost you points if you don't stick your landing, if you take a step, or if you fall. It cost you a great deal of points, and so you need to know exactly what to do in order to stick that landing. And here's some thicknesses of the mats and what it must be between. And so again, set of problems right here. Choose the correct scenario and fill out the table. Graph it, and then 4A and B and number 5, all the same kinds of problems that we've had in the past. Here we're going to be talking about hitting a golf ball in the moon, what the angle was, the speed of it per 100 feet per second, and the acceleration is 5.3 per second squared, and then the ball landed. And so which of these equations is going to work? Obviously in these 3 equations I'm going to give you some help with it. Sometimes it's a little bit difficult to see them. And then we're going to choose the function out of here, and the same problems over again. So I don't think I'm going to say anything more. I believe you can do these problems. We're not going to do the talk on this one. It's just a matter of filling out these tables over and over and over again, and I don't see a need. And so here we are at the end of the chapter, the summary, and we'll go over the summary in class.